Frazzled. I was in a meeting and I didn't get to read over my notes.
You got this. You do this all the time. This is
That's
your
true.
jam.
This is my jam. So I'm feeling fine.
I don't think you give up.
You've done great.
You can take a deep breath. Fair enough.
No. We're gonna keep going with our probability. I know, we could be having way more fun. But probability is pretty fun. And we're combining tree diagrams with probabilities. So last day we looked at tree diagrams to find the sample space, right? And then we were able to find probabilities associated with how many items satisfy the criteria out of the sample space. So we already used tree diagrams to list events in a sample space, okay? And what we're gonna do today is we're going to kind of level up just a smidge, okay? And so now what we're gonna do is we're gonna assign probabilities to each branch in a tree diagram, right? So instead of the counts or just saying what it is, what each branch represents, we're going to have some probability associated with each branch. Then, as we go down a tree, and I'll just pull up a tree from last day. Let's do this one maybe. Yeah. I think, oh no, this was from class. So we had a jar of 3 marbles labeled 1, 2, 3. Okay, and then we set up our tree to represent drawing 2 marbles without replacement. And so for our first marble, we had 3 choices, 1, 2, or 3. And then it didn't matter. We'd have 2 choices, but the choice would depend on the initial choice because we're drawing without replacement. So then we had 2 options, but they would change. Okay? What we did then was we looked at the sum. Okay? In this particular example that I just pulled out of nowhere, we looked at the sum of each branch. And then we wanted to find the probability that the sum of the numbers is 5. Okay? And so by listing the sample space, we have 1, 2, 3, 4, 5, 6 possible outcomes. Okay? And then 2 of those outcomes satisfy a sum of 5. And so then we found that the probability was 2/6. Now what we can do instead is we can assign probabilities, right? We have a probability of 1 in 3, right? 1 in 3 marbles, they're not, you know, different sizes or different weights or anything. We assume they have an equal probability. And so we split 1 in 3 chance. Then I move on to, then I only have 2 options. So now each of those have a 1 in 2 chance. But for this first branch, for a sum of 3, from the combination of 1 and 2, okay, then what we're going to do is we're going to multiply down this branch to get that probability of ending up at the end of each branch. Now let's go back to today. And, oh, it's all part of it. Okay. Let me just copy this, then crop top. We begin with an example. No, let's do this. Let's just say we have 3 marbles. And to eliminate any confusion, we'll just call them A, B, C, right? Instead of 1, 2, 3. Now, what we can do is we can say the probability of A, maybe the probability of drawing A, and now A can be anything, right? It can be, I don't know, marble A. It can be choosing a pizza over some other options, 2 other options, a sandwich or a soup. Man, I'm creative. Right, so then I have 3 initial options, and then followed by some other options. Anyways, the probability of A, we can say is maybe 0.6. Knowing that probabilities have to be between 0 and 1, right? So let's do a recall, because that's going to haunt us. Now, when I say P of A, I mean a generic P of A, right? And it's because A, B, C, D, blah, blah, blah. But P of A, so the probability of any event has to be between 0 and 1. It's 0 if it's never going to happen, and it's 1 if it will always happen. And then somewhere in between, there's some probability of it happening. And the probability of the sample space has to be 1. Otherwise, it's not the sample space, because then I haven't listed all the possible outcomes, right? And so if we think about, okay, if I have these marbles, let's say, because that's what we were working with before, right? Marble 1 can be either A, B, or C. Okay. What do we know about the probability of B and C? B and C, the probabilities here, they have to be add with 0.6 to make 1, right? Which means that I have 0.4 that I can split between these when I'm making up these examples. So what if I make the probability of drawing B 0.1, and maybe C then would be 0.30. So there's a higher probability of drawing A, and the lowest probability is drawing B. Right? That you could visualize that. If you have 100 marbles to draw from, right? You would have 60 that are labeled A, you'd have 10 that are labeled B, and you'd have 30 that are labeled C. Right? That's the easiest way to think about it. Then we can keep going. And let's say we flip a coin. We get heads or tails, and we know those probabilities. What's true about those probabilities as well is that they have to add to 1, right? If I flip a coin, one of those 2 events has to happen, right? And we assume that it's an equal probability. And so the probability of heads is 0.5, and the probability of tails is 0.5. So I pull a marble and I flip a coin. Who knows what we're doing here, but we're going to find the probabilities. It's like those math problems, right? You have 215 watermelons, that kind of thing. We're drawing a marble and we're flipping a coin. And bless you. Probability of heads is 0.5. Now, usually I get lazy and I don't write the probability aspect. I just say 0.5. So I just write what the probability is. Heads, tails, 0.5, 0.5. At the end of each of these branches, you can read this as A and H. So this is A and H. To find the probability of drawing a marble A and then flipping a head, you can multiply down the branches. So to find the probability of A and H, we can multiply down the branch. We've seen that before, right? When we say and, it's going to mean multiplication. So here I'll add that and is multiplication, whereas or is going to be addition. So instead of writing A and H, right, we saw in our child example, boy, girl, boy, boy, girl, girl, boy, boy, girl, right? We had 3 children, I guess. And we built that tree and we looked at all the possible outcomes and we can find the probabilities at the end of each of those branches. That would be pretty boring because if we assume equal probabilities, they're all the same, right? It doesn't matter. But the different outcomes, well, will be different. Now, usually how I shortcut this is I just write an AT. So AH implies A and H, AT implies A and T. So here is BH, here's BT, CH, and CT. Okay. So the probability of A and H in this case would be 0.6 times 0.5. So at the end of each branch, if you multiply down the branches, you would find the probabilities, right, of ending up at the end of that branch. And so maybe what I'll do is I'll snag a clean-ish copy of this. Clean this up here. AH. So if we go through and the probability of AH is 0.6 times 0.5. 0.6 times 0.5. These are still probabilities, and so they still have to be between 0 and 1. If you're finding something that's not between 0 and 1, then something has gone wrong. But I get 0.3, which means that the other branch would also be 0.3, right? 0.6 times 0.5 again is 0.3. Moving on to the next branch, 0.1 times 0.5 is, and this is how sloppy I usually get. Underneath, I just jot down what it is. I don't use any notation. Sloppy, sloppy, sloppy. 0.05. That's what's nice about using 0.5. 0.3 times 0.5, I get 0.15 and 0.15. What do we know about the sample space? The probabilities of the total sample space has to be 1. So one way that you can check your work is if you add these all up and you haven't done any rounding, right, then they should all add to 1. Make sure the sample space adds to 1, which hopefully it does. 0.6, 0.9, score. Another reason that is because A and H or A and T or B and H or B and T. So when I link these with ors, right, then I'm going to add up those probabilities. Now, if I'm kind of oring my way through all the possible outcomes, they should add to 1. Okay. We can also use this to find, and I know I'm getting ahead of myself, but it might be nice, the probability of flipping heads. Right. Overall is just 0.5. right? But if you want to incorporate each of the marbles and flipping heads, right, then you would have, you flipped a head here, or here, or here, right? And I know I'm getting ahead of myself, so I'll put a pin in it here. But we'll get there. Oh, I don't love what's going on the side there. I wrote a lot more than that. Add a page. Oh, what did I do? Copy. I made a copy, but then I forgot to paste it. Oh, phew. Okay. Good thing it's clever. We begin with an example, not quite. We already started pretty hard. Suppose a jar contains 3 red and 4 white marbles. If 2 marbles are drawn with replacement, what's the probability that both marbles are red? So now I have with replacement. And that's important. So I've got a jar of a total of 7 marbles, right? That's a good place to start. So 7 total. What's the probability of drawing a red marble? There are 3 red out of 7, and so the probability is 3 and 7. What's the probability of drawing a white marble? Well, there's 4 out of 7, so the probability is 4 and 7. If we draw our tree, that's not annoying. I said it's not annoying. I thought they'd be done working by now. I guess they just took the portable and moved it over here. Weird, right? Ugh. I don't like the portable. It's either too hot or too cold. And never good. Never just. Wasn't it crazy hot some days though?
Well, it was cold outside when we started.
Yeah, that helps. Maybe I was just moving around too much. So, my first marble number 1. We just said the probability of drawing a red is 3 in 7, and the probability of drawing a white is 4 in 7. Knowing the total number of marbles and what the distribution is really helps. Now, if they're drawn with replacement, right, then when I go in for my second marble number 2, doesn't matter what happened in the first marble, right? I can either draw a red or a white, and those probabilities are the same. Three and 7 and 4 and 7. Doesn't matter what happened at the first draw. We want to find what's the probability that both marbles are red. Now, the only way that I can make that happen is if I get a red and a red. All right. Let's jot down our sample space. I could draw a red and then a red, or a red and then a white, or a white and then a red, or a white and a white. The one I'm interested in is only satisfied by this first branch. So then the probability of R and R is going to be whatever I get when I multiply down the branch. And you can use your calculator. 3/7 feels like it's going to be a bad number. It is bad. You can just use your calculator. 3/7. If you are comfortable working with fractions, that's cool. You don't have to, right? Multiplying fractions is relatively easy. You can just multiply across, right? But let's just do, I'll just use my calculator. 3/7 times, or you could square it if you want, 3/7 as long as you use brackets. It is 9/49 in case you wanted to try your fraction work. Or 0.183673469 Yeah, so that's the probability of drawing a red marble followed by another red marble. Nice. And that's the answer. So if you want to use 9/49, cool. That's the exact answer. That's the exact answer. This is an approximation because presumably it keeps going. Such a mess. But I can only see that far.
So if it does say perfect replacement, would the numbers change? Like it would be 3/7.
Yeah, I'm confident that we have one. Do you mean without replacement?
Yeah.
Yeah, so I'm fairly certain we have one coming our way. It's something I would know or remember. Maybe, hey. It was the perfect segue. It's almost like I knew. If the marbles were drawn without replacement, then what's the probability that both marbles are red? So what I'm going to do is I'm going to steal this because we already did it. But I have to change. I have to change these probabilities, right? Because now it's without replacement. If I've drawn a marble and I'm not replacing it, my total changes, right? Now I have 6 marbles, right? And depending on what my first marble was, that's going to determine what the denominator is, right? And so if I've already drawn a red and there were 3 to start, then I have 2 left, right? 2 out of 6. Of those 6, the other 4 are still white, right? Because they're untouched. And it makes sense, right? Each kind of chunk of branches still has to add to 1. 2 plus 4 is 6/6 is 1. Nice. How about for the second set of branches, for if we draw a white marble first, then I still have 3 red marbles, but it's out of 6 now. And I only have 3 white marbles out of 6. So now, oops, the probability of R and R is going to be 3/7 times 2/6. Let's see here, 3/7 times 2/6. Let's see if it reduced to 1/7 for me. It does, it makes it all fancy. 1/7 or 0.142857149, which is different. Can I keep them on the same? If I move my pencil, whee, then we can have the two different scenarios, right? And so this here, when we draw without replacement, right, we call this a conditional probability. That's not until the next section, but I'm just telling you that we've already seen it, right? We just haven't, well, I guess I did put a name to it, get carried away. Because it's conditional on what happened in the first draw. Nice. Any questions about those? All right. More marbles. It's because they're the easiest to kind of imagine, I think. Suppose a jar contains 3 red and 4 white marbles. It's the same jar. If 2 marbles are drawn without replacement, find the following probabilities using a tree diagram. So we already have this tree, so I'm going to snag it because actually, no, let's start fresh. Without replacement, let's see here. Let's draw our general bag of marbles. That should be a red and a white marble. And there's 3 out of 7 or 4 out of 7. It's marble number 1. Without replacement, we decided that, okay, well, let's keep track of this because now I only have 6 marbles, right? And 2 out of those 6 are red. And the remaining 4 out of 6 are white. If I drew a white marble initially, then I still have the 3 red marbles out of 6, and I have 3 out of 6 white marbles. Marble number 2. I'm going to copy this. You can probably do it all on the same graph. Oh, wait, we're not done here. Sorry. What I like to do before I even read all these questions, because I can tell even if we kind of peruse here, we're going to need to find a couple of probabilities. And so what's nice, or what I find nice, is if we multiply down all the branches, right? Just to make sure that we have all the probabilities already. And then I can make sure that they add to 1 as well. So that's a nice way of making sure I'm on track. But we said this was, oops, 0.14286. I'm rounding to 5 decimal places. It's too long. When I do rounding, I can be there's a little bit of wiggle room on the adding to 1, depending on how I've rounded, right? But kind of within reason.
Is it just better to keep it as a fraction, or do we have to put a decimal?
You don't have to put a decimal. I just find that most people like decimals better, but you can keep them as fractions. That's great. For the next branch, 3/7 times 4/6. I get 2/7 or 0.28571. For the next branch, I have 4/7 times 3/6. Get 2/7 again. Yeah, that works. 0.28571 and 4 divided by 7, not times 7, times 3/6. I get 2/7 again. Did I do that right? Yes, 8571. Now we can check that the sum is equal to 1. So 0.14286 plus, and I'm gonna do 3 times 0.28571. I get 0.99999, but that's just from rounding. Close enough. Nice. So then I can feel good about the values that I have, at least that I'm about to be working with. Now I'm going to make a copy. Copy. Paste. I'll remove this. Copy. We already answered A. The probability that both marbles are red is equal to 0.14286. Rounded, I guess. Can I just say from the previous question? Because we just did it. I don't know why we'd have to do it twice. B should be better. We want the probability that the first marble is red and the second is white. Now, the only way that that can happen is through this branch. So what we write is we say the probability of R and W is 0.28571. Finally, we get into some juicier questions here. Juicy. We want the probability that one marble is red and the other is white. Why is this juicy? It's juicy because just came in from the hallways. Because it can be either red then white or white and red. I happen to know that someone already taught you this really, really well.
Oh my gosh, I wondered.
So
That's not.
it's not fair.
It's not about being fair.
So it's, let's see here. this or this. And when we say or, we add those probabilities. And so the probability of, let's see here, how can I shorthand this? 1 R and 1 white is going to be 0.28571 plus 0.28571. 0.28571 times 2 is 0.57142. Nice. So or is what gives us this addition. Nice. Any questions about that one? You don't get a say. But I like like, all right, moving on. It's easy for me. Mhm. Yeah, because those were 2/7, right? Yeah. So, or I should say, or 4/7, if you are fancy like that. And 4/7, yeah. Ah, yes, indubitably. Can't even say that. What if instead of 7 marbles, you had 70 marbles and you were gonna draw 15 marbles? Yeah, it's a terrible tree diagram, tell you that much. Even if they're only red and white marbles, right? If we're drawing 15 marbles, which isn't even that many, right? And we want to find probabilities of, well, what's the probability that there is a red one in there? What? You don't want to do that, right? You don't want to do that with a tree. You can do it with a tree, but it sounds just terrible. So you can use combinatorics or combinations, right? Which is the choose function. Sneaky, sneaky, sneaky. And so here, what we're talking about, the combinations that they're referring to is the choose function, right? NCR or something like that on your calculator. From n items, choose R of those. Choose function, which is n factorial over n minus r factorial times r factorial. It was a bonus on your test. It was, but now on the final exam, a real question, of course.
You appreciate that. Very nice.
I'm still bothered by it said 1 mark and then 1 marks for the second one. Clearly I had it at 2 and then I forgot to change the grammar. Busted. Felt like a lot of bonus marks. Okay. Suppose a jar contains 3 red, 2 white, and 3 blue marbles. Not really showcasing why we would need the choose function. I think we can still solve these with a tree diagram. But if 3 marbles are drawn, right now you have 3 layers of your tree and it gets, a little bit out of hand. You can still check your answers with a tree in this scenario, and that's nice, but we'll just use the choose function. And so we have 3 plus 2 plus 3 is 8 marbles, right? Nice. And if 3 marbles are drawn without replacement, then we're going to find these probabilities. We're going to find the probability of 2 red and 1 white. Now, what we needed before was to know the total number of possible outcomes. Okay, and so I have total of 8 marbles, and I'm going to choose 3 of those. So choose 3. And we're going to look at specific combinations, but first we need to figure out how many ways out of 8 marbles can I choose 3 of them, right? And so we first need to determine how many ways we can choose 3 marbles out of 8. And that is where the choose, oops, I guess I should choose. That's going to translate into 8 choose 3. And I should have started a next page, I think. We can use the factorial formula just for practice. 8 choose 3, or let's do the general factorial formula first. NCR is n factorial over n minus r factorial times r factorial. Pretty sure. The confidence is overwhelming. Let's see here. Go to your trusty formula sheet with that beautiful gradient. Nailed it. Okay. So we can use the formula 8 factorial over 8 minus 3 factorial times 3 factorial. 8 minus 3 makes 5, so I'm going to expand 8 factorial until I hit 5 factorial. 8 times 7 times 6 times 5 factorial over 5 factorial times 3 factorial. Those guys will cancel. And what's cute is 3 factorial is 3 times 2 times 1, which is 6. So 6 and 3 factorial will also cancel. And I'm left with just 8 times 7, which is 56. This is the total number of ways that if I ignore the colors of the marbles and everything like that, this is the total number of ways that I could pick 8 marbles or pick 3 marbles out of 8. So here, ignoring colors, there are 56 ways to choose 3 out of 8. That's going to become our denominator and our probability. How can I use so many arrows? I'll just write that out. This will become our denominator in our probability. Right? How many ways? If I'm drawing 3 marbles, there are 56 ways that I can do that. And now we want to figure out, well, how many ways satisfy the one that we're interested in? So next, we need to find the number of ways to pick the three of interest. 56 is going to be our denominator for all of these. And now we need to find, okay, well, how can I choose 2 red and 1 white? So I need to choose 2 red and 1 white. Let's focus on the 2 red. How many red ones did I have? I have 3 red. And if I need to pick 2 of those, right, I need to choose 2 out of those 3, right? And so 2 red is going to be from 3, choose 2. Okay. Because we had a total of 3 red, and I need to choose 2 of those. And then we have 2 white ones, which 1 white. So then from these 2 white ones, I need to choose 1. To choose 1. And means I multiply those 2. So this becomes 3 choose 2 times 2 choose 1. I would say you can do it with the factorial formula, but you can just use your calculator, right? 3 choose 2. Otherwise, it's a lot of just multiplying, canceling, and another multiplication, and then division. Ew. Let's try it on your calculator. 3 choose 2. Just make sure that you get the same numbers. Oops, 3. Which means that there are 3 ways to choose 2 things. And to choose 1, it's usually 2. So 3 times 2 makes 6. Which means that the probability of 2 red and 1 white, 6 out of 56. Right. Nice. Okay. I need another page. One of each color. Now I have to force one of each color, and that's going to exhaust my 3, right? If I was drawing more than 3 and there were 3 colors, right, then there would be other options. But because I'm only drawing 3 and there are 3 colors, that is going to be 3 choose 1, right, for my red. Right, 3 red, 2 white, and 3 blue. And 2 choose 1 for my white, and 3 choose 1 for my blue. Let's bump this down a little bit. Red, white, and blue. And from the white ones, oh, I've already forgotten 2, I think. 2 white and 3 blue. Okay. 2 choose 1 and 3 choose 1. 3 choose 1, can try it, is 3. 2 choose 1 is 2 and 3 choose 1 is 3. 3 times 2 times 3 makes 18. Oh, and I guess let's be proper about it. How can I be proper about it? This whole time, these should have all been over 56, since I attached it to the probability. Since I linked it to the probability already. Yeah. What if none of them can be blue? Hmm. If none of them can be blue, how many do you have to choose from? And it doesn't matter if they're white or red, right? I have 3 red ones and 2 white ones that I can still choose from, right? And I can choose 3 from those 5. So this is going to be 5 choose 3, right? Because it can be red or white. There are 5 total. Right, just exclude the blues that you don't want. Divided by, technically 8 choose 3, but we've already solved it to be 56. So we'll just keep 56. Nice. I think that one's kind of a sneaky one, right? Have to think about, okay, if none of them are blue, right? Otherwise, you'd have to list all the possible outcomes of drawing 3 marbles, right? Where none of them are blue, right? Could be 1 white one, 2 red ones, 1 red one, 2, or that's the same, 1, 2 white ones, 1 red one, 3 red ones, and so on and so forth. And you'd have to throw an or in between all those. That's a lot of work, right? So using the combinations in this case is a little bit simpler. At least 1 blue. What can we do here? Oh, I guess I should finish this. 5 choose 3, let's see here, is 10. 10 out of 56. Hmm. How are we going to tackle this? At least 1 blue. At least 1 blue. Well, be 1 blue or 2 blue or 3 blue. And then all the different combinations around that. That's hard. What if we took away the ones we don't want? Which we already have, right? At least 1 blue, then I already know that that should be now none blue. It's only because I have the solutions and I'm staring at them. Nope, it works. Crisis averted. Whew. Okay, so my go-to trick is as soon as I see at least, I usually don't want to do that, right? Because we can think of it as, okay, so at least one blue is one blue and two non-blues. Oops, not plus, I should say, and two non-blues. Can I say non-B? Or two blues and one non-blue. Or three blues. Right? Or. We could find all those probabilities, right? One blue and two non-blues. That's going to be from three blues, choose one times, how many non-blues are there? There's five. Five, choose two, plus, and so on and so forth, blah, 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 blah. You can tell, I just don't feel like doing that. It's really annoying and boring. Well, not boring, it's tedious. Which I usually like. Usually I like tedious things. So that means I can feel good about what I'm doing. I know what I'm doing. But at least that triggers me into thinking about, okay, well, what about the complement? Right? Usually it's easier to calculate the complement. So when we see at least, it is usually easier to consider the complement. Which would look like what? The probability of at least one blue is going to be a 1 minus, well, what's the opposite of at least one blue is that there are no blues. 1 minus the probability of none blue, which we already have. From the previous part, we said it was 10 over 56. So then I get 1 minus 10 over 56. Or if you're going to do kind of by hand calculations, right, you would multiply the 1 by 56 over 56, which is going to be 56 minus 10 all over 56, which is 46 over 56. You can do all this work, but what you will find is that your final answer will be 46 over 56, right? And so I encourage you to try it just to kind of get flexy, but then whenever you see at least, have a little trigger that says, and there's probably a quicker way to do this, right? By taking the complement. Nice. Any questions about that one? No. Deck of cards. 5 cards are drawn from a deck. Find the probability of obtaining 2 pairs. So 2 cards of one value, 2 of another value, which has to be different than the other pair. That's kind of implied because otherwise it's not 2 pairs. It would be considered 4 of a kind, right? And so they have to be of different values, and 1 other card. So in your hand, you would have 2 pairs. Oops, sorry. A pair, and 1 other card. This means that you've drawn 5 cards, bless you, from a deck of cards, which I'm going to tell you in case you are not sure. There's 52 cards in a deck of cards. I've had students come up to me after class and say, I don't know anything about cards. How am I supposed to solve these problems? And there are some go-to things that we should know, like 52 cards in a deck. But otherwise, I tend to stay away from card problems on a test just because it can be difficult. And I don't really expect you to know cards. On an assignment, though, you can do it. Okay, so this is 2 cards. This is 2 cards, and this is 1 card, which means I've drawn a total of 5 cards. Why do we need to know that? Because just like before, we need to figure out, well, how many ways can I draw just 5 cards, right? And then this scenario is going to be one of those, or some number of those 5 card draws. So first we need to figure out of 52, so the total number of 5 card hands is going to be 52, choose 5, right? It doesn't matter just how many ways could I draw 5, a hand of 5. So 52, choose 5. And I'm just flat out using my calculator now. You can use the factorial formula, but 2598960. It would still involve a lot of multiplying, and so I don't really see the point. So there are numbers 1, 2, 3, almost 6 million ways to draw a 5 card hand. Yeah.
On a test, are you gonna tell us to like show your work using that formula? Or if you don't say anything, can you just use it?
Yeah, if I don't say anything, like on the bonus, what did I say? On the first bonus, it says use the factorial formula to compute this, so then you would have to. But on the second one, I just asked you to show me how you got there. And so then it doesn't matter. But if I specify, yeah, but I will specify, yeah, if I need it. Where in this scenario, I don't need it. Okay, did I do my commas right? Dink, dink. Yeah, roughly 2.6-ish million 5 card hands. Yikes. How many of those are 2 pairs and 1 other card? Let's see. How can I draw? And I'm going to need to cheat, I think, or at least. Or at least think about it. And she's confusing sometimes. I'm just gonna do it how I was going to do it. And ignore her for a second, and maybe they'll work out to be the same thing. Maybe,
Sounds like a plan.
right? Like maybe tune out for a sec. Uh, maybe. How do we get a pair? There are 4 of each card. I'm thinking a pair of aces, for example, right? First, I wanted to go across the suits, but that doesn't make sense, right? And so within each pair, I have four things to choose from. So one pair would be 4, choose 2. And then the other pair would be a different 4, choose 2. And then the one card, how many do I have to choose from? I need to choose one, I know that. So let's start that. But the pickle is, how many do I have to choose from? Now, the problem is, it can't be one of these cards, right? Because then it would be 3 of a kind instead of a pair, right? And so we've effectively excluded 8 of the 52 cards, right? Otherwise, it would change the shape of our hand, right? And so here, this is going to be 52 minus 8, which is 44. Right, 52 minus 8 is 44. That don't match any of the pairs. Need more room. Okay. So to get this 2 pairs and 1 card, I would have to have 4, choose 2 and 4, choose 2 and 44, choose 1. So far, I'm on board. Divided by 52, choose 5, or we already solved it, 2, 5, 9, 8, 9, 6, 0. Yeah. Thank you. Nice. That's going to make a difference for sure. 4, choose 2 is 6. 4, choose 2 again is 6. And 44, choose 1 is 44. I think we're seeing a pattern with the choose 1. 2, 5, 9, 8, 9, 6, 0. In fact, it's called Pascal's triangle. You can map out all the choose functions. It's pretty cool. You guys heard of Pascal's triangle before? No. Well, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. What? It just keeps going forever and ever and ever. But what this does is 1, 2, 3, 4. choose 1, no, 1, 2. I don't remember how it goes. 4, choose 2. We're supposed to get to 6. I think it's here. 1, 5, 10, 10. No, it is this one. 4, choose 2. I just can't get there. Anyways, these are all the choose functions. Somehow. Oh, because 0 is an option. Okay, so 0, choose 1, choose 2, choose 3. So this is your R. And then this is your, let me pick the right one. N equals 1, N equals 2 line, N equals 3 line, N equals 4. 4, choose 3 is 6. Or sorry, 2. I said the wrong thing finally. But if I highlight it. Before calculators, obviously, this was useful. Now, our calculator just did 52, choose 5, no problem. So we don't really need it anymore. Yeah, I'm sure pretty quickly they probably printed it so that people could just have it. Then you'll have it. They probably made a copy, just like all the old school tables and stuff. But it's called Pascal's triangle. I took computer science one time. It was terrible because we had to program Pascal's triangle. I just couldn't get there. Now I do a lot of programming, but then I couldn't do it. So I dropped that course. My dad's a software engineer, and so I'd go home for help. And he's also Swedish, so he's like very quiet and blunt. And so one time he's helping me and he's like, Emily, I think computer science is not for you. That's fair, I just need to pass this course. Yeah, just squint. That was his math advice. Just squint harder. And now I do find myself wanting to say that sometimes. Well, just like look at it harder. I don't, but
In your mind.
sometimes. Like just squint. It's me crying at the kitchen table.
I
Oh,
wasn't squinting, it was through
Yeah,
tears.
yeah.
my child.
Oh,
I need to-
and then I did a math degree, so it can't have been that bad. 2, 5, 9, 8, 9, 6, 0. Oh boy.
Oh, you-
No.
I was like, was there also a belt on your kitchen table? 'Cause there was on.
No. No, can't say there was.
A hanger? That's-
I thought it was a flip-flop.
That too, but that's long range. That's-
Oh.
You gotta feel that.
No. So like I said, how bad could it have been? All right. No.
You'll never know.
This is for a suit, right? 4, choose 2, right? 4, choose 2, but we have different suits that we can choose from. And this is where she's kind of lost me. To find the probability of obtaining two pairs, we consider all possible pairs. I can get there, but
No, her way.
13.
she says aces, deuces, and so on. I don't think so. But there are 13 choose two, different combinations of pairs. We think on it for a bit.
That makes sense.
That does make sense
There's 13 options in each.
in each
What are they called in English?
suit.
Suit, yes. I knew that.
I know. I always call the one just a clover.
Yeah.
Oh,
Yeah.
Yes.
Yes. And that's by elimination because the other one's a spade,
Mhm.
which translates, but then, yeah, clover. Okay. Can we just accept it and then move on?
You're not paying this one on the test, are you?
No.
There's-
If I can't even work my way through it, I'd be happy with this. Two pairs and one card. That's a really good, that's a job well done. It's a really small probability. So I think I'll just leave it there. It's like times 10 to the negative 4.
Why did you do 13 choose two? Because there's no pairs in one suit.
Mhm. Oh, but you could have a pair of
A pair of
aces or a pair of
suits.
threes, pair of twos, pair of fours, working through all the different 13. I think I'm getting there.
Mhm.
Okay, obviously not on the test, so just take a nap or something. But let's just say we have 13 choose two different pairs.
Let's just do it for fun.
So then the probability of two pairs and one is 13 choose two times that probability that we found. And then I give up. The birthday problem. Have you guys heard about the birthday problem before?
No.
So in a relatively small group, I guess, yeah, spoiler alert, in a relatively small group of people, the probability that two people have the same birthday is actually quite high.
Oh, really?
That's called the birthday problem.
Why is it a problem? Can't we all just celebrate that we have-
Only I. I've never met someone with that birthday.
Really?
June 5th.
My mom has that birthday. I know people that have that birthday.
I was gonna be like, I need to eat your mom. with that. That's not gonna sound very good.
Mine's April 30th. Any takers? No?
No.
Same as the King of Sweden. So that's kind of
Wow.
nice.
So
Mhm.
you're practically royalty, is what you're saying.
I mean, basically, right? I know. It's kind of a small group. I think we have to hit 20 or so to get a 50% probability. So pretty good.
Wow.
I know, right? Well, just hold tight.
So I'm not excited, but I was like, we felt like celebrating,
Mm,
making a math problem. right?
party time.
That sounds like a math.
Yeah, well, a cell phone store
Anyways.
Great segue, yes.
receives a shipment of 15 cell phones that contains 8 iPhones and 7 Android phones. Suppose that 6 cell phones are randomly selected from this shipment. Find the probability that a randomly selected set of 6 cell phones consists of 2 iPhones and 4 Android phones. Now we're back to questions that I do expect you to be able to do because this is perfectly reasonable. Why? I know that I need the probability of 2 iPhones and 4 Android. I also know that I'm out of 8 iPhones, I am picking 2 of those. 8 choose 2. And, so I multiply. Out of the 7 Android phones, I'm choosing 4 of those. Feels good to be back on solid land. Now, before, we were figuring out how many total possibilities there were kind of before we started the problem, but this is just one problem. So we can just do it in the denominator. So out of 15 cell phones, I need to choose a set of 6 cell phones. And like before, I encourage you to just use your calculator. 8 choose 2 is 28. And 7 choose 4 is 35. And 15 choose 6 is, oops, 5,005. 28 times 35 is 980. Divided by 5,005. I get roughly 0.195804198. That's a question that I do expect you to be able to tackle. The other one, I don't know, made a miss. Wait,
No, it's all right.
she survived it. One afternoon, a bagel store still has 53 bagels remaining, 20 plain, 15 poppy seed, and 18 sesame seed bagels. Suppose that the store owner packages up a bag of 9 bagels to bring home for tomorrow's breakfast. A little bit TMI, I think, and selects the bagels randomly. They're really going for it. Find the probability that the bag contains 4 plain, 3 poppy seed, and 2 sesame seed. Another one where I would expect you to be able to handle something like this. We want the probability of 4 plain and 3 poppy seed and 2 sesame. From the 20 plain, I choose 4. And from the 15 poppy seed, I choose 3. And from the 18 sesame, I choose 2. Divided by, I have a total of 53 bagels. And I'm choosing 9. 4 plus 3 plus 2 is 9. Choose, oops, wrong. I hit something. 20 choose 4. I'm going to bump this over as 4, 8, 4, 5. 15 choose 3 is 455. And 18 choose 2 is 153. 53 choose 9 should be quite large. 4, 4, 3, 1, 6, 1, 3, 5, 5, 0. $4,845 times 455 times 153. I get a nasty number, 337,284,675 divided by this mumba jumba, 4,431,613,550. Get 0.07612595213. Birthday problem. Ah. Any questions about this one before we go to the birthday problem? Which there are videos about the birthday problem. So it's kind of like a well-known problem. If there are 25 people in a room, what's the probability that at least, when I see at least, right, I want you to be kind of thinking, okay, probably the complement is going to be the way to go, and it will be, that at least 2 people have the same birthday. And so here, consider the complement of at least 2 people having the same birthday is that no one has the same birthday, right? Which is no same birthdays in a group of 25. Let's start with the denominator and figure out, okay, well, if I want the probability of no same birthdays, that's going to be out of the total number of ways, or all the different birthdays. 25 birthdays. Right. How can we figure out how many birthdays there are or can possibly be in 25 people? You could use your slots, 1, 2, 3, 4, 5, 6, 7, blah, 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 blah. 25 slots, each having 365 options. Let's assume no leap years, blah, blah, blah. If you got a leap year birthday, you're out of here. Bunging up our birthday problem, right? So 25 birthdays. This is going to be 365 to the power of 25. That's how many total possible birthdays we could have, right? Or combinations of birthdays, which is probably, I wouldn't be surprised if it didn't like it at all. Okay, it's quite large, but it's still doing it. Okay, let's just keep it at 365 to the power of 220, or to the power of 25. That's going to be our denominator, right? All the possible birthdays. Now, that's if they're allowed to have all the same birthdays. We're not restricting it in any way, right? What about here? What about no same birthday? In terms of our slots, 1, 2, 3, 4, blah, 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 blah. Our 25 slots, what would that look like? I have 365 birthdays to choose from for the first person, but then no repetition. 364, 363, 362, blah, 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 blah. And then I don't want to do the math. This is the same as 365 P25, right? Permuted 25 ways because the it's decreasing, right? The number of options are decreasing. So what we have for the probability of no same birthday, I have 365 P25, which you have a P button on your calculator as well, over 365 to the power of 25. 365 P25 permuted onto 25 things is still very large. How about I just skip to the good part? Divided by 365 to the power of 25. Hey, yeah. It didn't like it. P25 divided by 365 to the power of 25. Step down the bracket. Ah, a nice, very reasonable probability of 0.431300296. If I tell you the probability that 25 people, there's no same birthday is 0.43, then your brain says, aha, but then the probability of at least a pair of birthdays is 1 minus that, right? Maybe. Therefore, the probability of at least, what were we calling it? 2 people have the same birthday. Having the same birthday. I need shorthand for that. Is going to be 1 minus the probability of no same birthdays. So the key is to figure out, well, how many ways can I have none of the same birthdays? And then I can do 1 minus 0.431300296. So then 1 minus that guy. The probability of at least 2 people having the same birthday is 0.5686, whoops, 99704. Pretty fun. Let's just in a group of 25. We're ignoring leap years, but I think everyone's any leap year people in here. No. And that's it.
That's not bad.
And I give up.
Twice a month.
What is the next section? Just out of curiosity. Conditional probability, we basically already did it. I'll pick up there. If you have any questions, let me know. Otherwise, enjoy your weekend and get ready for the last week of classes. Wow.